Did you get stuck when you tried using L'Hopital's rule to solve this limit? Be sure to stick around until the end so you can become a ninja who will crush this on your next exam. Notice that for L'Hopital's rule, if you remember, the first thing we'll do is we'll try plugging in 0 for x anywhere we see an expression of x, giving us sine of 0 minus 0 all over 0 cubed. And when you simplify this, you're going to get one of the indeterminate forms, 0 divided by 0, where in this form, you're allowed to use what's known as L'Hopital's rule. So what are we doing, right? We're basically saying, okay, I'm going to let the numerator be something I'm going to call g of x. So that numerator was sine of x minus x. And then when I take its derivative, I'll be left with cosine of x minus 1. And then similarly for the denominator, I'm going to call it h of x. So the original denominator was x cubed, and after you take its derivative, you get 3x squared. And if you remember with L'Hopital's rule, what is it saying? If I have a limit expressed as a ratio here of g of x over h of x, and when you plug in 0 for x, you get one of the indeterminate forms, it's the same as having the limit as x approaches 0 of using the derivative functions instead. And I'm going to go ahead and do that here. And this is maybe where you got stuck, right? Because for the original problem now, when you tried solving it, by using the derivative functions we found for g and h above, now when you plug in 0 for this new expression, cosine of x minus 1, all over 3x squared, look at this. When you simplify this further, you're going to run into this issue, right? Because for the numerator, it's going to become 1 minus 1, and that's just simply 0. And then when you divide it by 0 on the denominator, what do we do here? We've got another indeterminate form. And maybe you threw your paper across the table and you're like, you know what, ninjas? I'm sick of this problem. I'm done. But hang on a second, let's work through this together, because you went in the right direction using L'Hopital's rule here, but no one said you couldn't do it again and possibly again and again, as long as you remember that if you want to use it again, you still need to have one of the indeterminate forms that are allowed. So because we ended up with 0 over 0 once again here, this means that with this indeterminate form, why don't you just use L'Hopital's rule once again? Because notice how the terms are simplifying, and eventually we might get to a solution where when you plug in 0 for x, you're going to get a value that is your final answer. So now what I'm going to do is I'm going to let this new numerator g of x be cosine of x minus 1, and the new denominator is going to be 3x squared. And then for both, when I take the derivatives once again, for the new numerator's derivative, you get negative sine of x. And for the denominator's derivative, you'll get 6x. So going back now, what I'm going to do next is by taking this expression we got after applying L'Hopital's rule once, now when you use the second application of L'Hopital's rule, with the new derivatives, you are now going to evaluate this limit as x approaches 0 of negative sine of x all over 6x. And maybe this is where the frustration builds, because as you'll see, when you plug in 0 here for x, we're once again going to end up with 0 over 0. But stick with the problem. Don't give up just yet, because look, we have another indeterminate form where we are allowed to use L'Hopital's rule again. And by the way, in this video, I know I'm focusing on L'Hopital's rule, but it actually isn't the fastest way to solve this problem. There's a quicker and better way. So let me know in the comments below if you see it. But moving on, for this limit now, negative sine of x over 6x, by inspection, because it's a lot easier to work with, I'm just going to visually see that the denominator and numerator, when you take their derivatives, are pretty straightforward, right? You'll get negative cosine of x as a new numerator, and for the denominator, you'll get just 6. And check this out. Now when you plug in 0, you're going to have an expression where when you evaluate this, you don't get an indeterminate form anywhere. You actually get the final answer. And then for this next problem,